France. I am Sebastien. Okay. Sorry. Yes. The record. Yes, I am in France, and the special information, maybe it's important for you. I work at Électricité de France, EDF. So I should know a lot about demand, electricity demand. But to be honest, today we're going to talk about modeling demand response. A field I know, but not in the way you look at in your different papers. I mean, I am more on the side of optimization and bottom-up model. So today I read the 4 abstracts, and I think it's based on statistics, on the field of statistics. If I am not wrong, there are machine learning, but I think machine learning is in this field. And we will start with Anna Genave from Île de la Réunion. And let me have a look at the abstract again. It's the electricity demand elasticity in Mauritius, an island not far from Île de la Réunion, with an ARDL bounds test approach to cointegration. If you don't mind, I will let you talk, and you could ask questions, and I will ask you question at the end of the presentation, because I've got some questions.
Of course. Of course. Thank you for the introduction. Now I am going to share my presentation. Do you see my presentation?
Yes.
Yes. Okay, hello everyone. So my name is Anna. Today I am going to talk about the electricity demand elasticity in marshes. So basically what motivated the study is the lack of understanding of a relationship between electricity consumption and some of the key economic variables in marshes, and these have important public policy implications. So a bit of context before proceeding to the model that I have estimated. Well, in figure 1, you can see the evolution of electricity consumption between 1990 and 2019. And what we can see is that consumption has increased at an average annual rate of 5.3%. But also what we do know is that electricity consumption represents only 25% of total final energy consumption in marshes. So now we want to understand what actually drives electricity, and then determine what are the main drivers of electricity in marshes, right? So if we look at electricity consumption in the different subsectors of the Mauritian economy, what we can see is that there has been an increase in household electricity consumption, growing at an average annual growth rate of 5.5%. So this can be explained by higher living standards and increased income for the household sector. Regarding the commercial sector, which comprises mainly of service-oriented sectors such as financial services, wholesale and retail trade, but also tourism. Well, we can see that increasing demand results mainly for needs from lighting, air conditioning, but also refrigeration and electronic equipment. So this increase in electricity consumption in the commercial sector has witnessed a more rapid growth compared to the household electricity sector. And we do know that electricity is the primary energy source for the commercial sector, highlighting its strategic importance for the sector. And now moving to the industrial electricity consumption, comprising mainly of manufacturing and construction consumers. Well, in the 1990s, what we see is that the industrial sector contributed to more than 50% of the total sales volume, but then in 2019, electricity consumption was almost evenly split between the three sectors. So the slow growth rate witnessed in the industrial sector can be explained by the higher added value production and the adoption of more efficient processes, right? So now we can see that there's some kind of potential explanation between the electricity consumption and some key economic variables. So the main research question here is, what are the main drivers of electricity consumption in Mauritius? But beyond that, what we want to do is to determine the nature and the magnitude of the relationship between electricity consumption and its main drivers. And also beyond this relationship, we want to know if there is a long-run equilibrium path for electricity consumption. If so, how does electricity consumption behave when it deviates from its long-run trajectory? And also, what are the potential implications for public policy, knowing that Mauritius is embarking on an energy transition process, notably through energy efficiency measures. So we want to understand how responsive electricity demand is to changes in key economic variables. So a brief overview of the literature. Now, this summary table indicates some of the studies, of course, is not exhaustive. But what I wanted to share you is that there are two types of studies: so single country studies focusing on only one island, but also we have multi-country studies using panel data. So to the best of my knowledge, there is only one study focusing on Mauritius, and that was Sultan in 2012. So he found multiple causal relationships running from and to electricity consumption per capita. And then you have other studies by Narayan Singh and Katur Sublu, focusing on Fiji and Singapore. Both found unidirectional causalities running from energy or electricity to GDP, but also to imports. So what kind of implications could there be for public policies? Well, if there is unidirectional causality running from energy or electricity consumption to GDP or imports or other explanatory variables, then putting in place the implementation of electricity conservation policies might be detrimental to economic growth or trade benefits or offset trade liberalization policies, right? And then when we do focus on multi-country studies, well, although insightful, these studies do not really provide the specific driving forces of islands. So whether one looks at specifically at islands or other groups of countries, the conclusion is always the same. When it comes to whether electricity consumption or energy consumption is a result of or a precondition of economic growth, well, there are no clear patterns in the literature. Although there is substantial empirical evidence, we do not agree on the nature and the magnitude of the relationship between electricity and other key economic variables, but also we do not have a consensus regarding the direction of causality. But I do argue that given the importance of electricity as a strategic commodity, but also the public policy implications, I do argue that it is important to investigate the nature of this relationship, given the paucity of literature on Mauritius. Now, a word on the methodology. While the objective is to estimate the short-term dynamics and the long-run equilibrium relationship for electricity consumption, which is our dependent variable, denoted TEC-PC, by using annual data points covering the period 1978 to 2019. So we have 42 observations. And then when selecting the explanatory variables that could potentially explain the changes in electricity consumption, well, according to literature, but also based on classic demand theory, we found that real GDP per capita, denoted GDP-PC, and average price of electricity denoted EP, are classic standard variables that are used to explain electricity consumption. But then when talking about exports per capita, regarding the outward-oriented strategy adopted by Mauritius since its independence, we get a sense that increased output from these sectors, mainly export-oriented enterprises, might drive electricity demand upwards. So if we look at figure 3, time series that are expressed in natural logarithms, we can see that our series might be potentially affected by trends and are potentially co-integrated, meaning that they move together in the long run, right? So we need to carry out formal tests to check whether our series are stationary and non-stationary. So stationarity essentially means that the series have constant means and variances over time, but when we look at our time series, we can't actually make that assumption. So we carry out what we call unit root tests. So we have either purely IO, which means purely stationary variables, but in the case of economic variables, what has been found in the literature is that normally economic variables are not stationary variables. So we can have either purely I1, which means purely non-stationary variables, but also we can have a mix of stationary and non-stationary, the mix of IO and I1. And in this case, we need to estimate an ARDL, which stands for autoregressive distributed lag bounce test approach to cointegration that was developed by Pasaran and his colleagues in 2001, which helps us to determine whether there is cointegration or no cointegration. So why cointegration is important is because when you have non-stationary variables and you regress them, you can have spurious regression, which means that they may be associated, but their correlation is nonsense. So that's why we want to test for cointegration. Once we prove that there is indeed cointegration and the existence of a long-run equilibrium relationship, we can estimate the autoregressive distributed lag error correction model. I know it's a mouthful. So this model helps us to estimate both short and long-run elasticities for electricity consumption. And as a complementary test, we run the causality test to know the direction of causality, either running from or to electricity consumption. And we adopted the Toda Yamamoto causality analysis, which is assumed to be superior to the traditional Granger causality test. We proceed to estimate the augmented vector autoregressive model to determine whether there is causality or not, right? So this is the empirical setting of the ARDL ECM. So essentially, what this first relation is telling us is that when you take electricity consumption in its first difference, it can be explained by its short-run dynamics. So all of the delta parameters that you see, which means first difference, and it can be also explained partly by the long-run equilibrium relationship. So the ECT -1, which is highlighted in green, is the error correction term, which gives us the co-integrating relationship, so the long-run equilibrium relationship between electricity consumption and our independent variables. And then you have the psi tech PC, which is the adjustment parameter, and it indicates how fast or slow electricity consumption is going to converge back to its equilibrium trajectory following a disturbance or exogenous shock. So essentially in relation to, we have expanded ECT -1, so the error correction term, which represents the deviation of electricity consumption from its long-run equilibrium. So as a complementary test, like I said before, we have a Toda Yamamoto causality analysis, and we are going to carry out this test on the first K optimal max as highlighted here. So for instance, if you have eta 2i, which is equal to 0, then we say that GDP-PC, so GDP per capita, does not range cause tech PC, electricity consumption. So essentially what does that mean is that if we do not reject the null hypothesis of causality, then it means that the knowledge of the past of GDP per capita does not help to predict electricity consumption and vice versa. So let's move into the results. Well, I'm not going to describe the whole table, but just know that when carrying out the unit group test, so we have ADF, PP, and KPSS, which are the usual unit group tests used in the literature. So in green, when you have green frames, it means that we fail to reject the null hypothesis. And when we have the red frame, it means that we reject the null hypothesis. So from our variables in levels, we know that they are non-stationary, as we assumed earlier. And then when we take the first differences, we confirm that they are non-stationary in levels, but they are integrated of order 1, which means that for them to become stationary, we have to difference them once. So now proceeding to the cointegration test to know whether there is indeed the existence of an equilibrium relationship. So from this table number 2, we can see that we have only one cointegrating relationship by means of the F statistics, which is highly significant at the 1% level. So we conclude that we have a steady state relationship, a unique integrating vector, and we also validate the weakly exogenous hypothesis, which enables us to actually estimate only one dynamic equation when electricity consumption is the dependent variable. So moving on to the results, now focusing on the short run elasticities. So from the upper part of the table highlighted in blue, what we can see is that electricity consumption is explained by its average price and exports, but electricity consumption remains inelastic to all of to the changes in all of the explanatory variables in the short run. For instance, if you look at the coefficient of electricity price, which is significant, but also according to literature is so the range of not the range. I mean the negative sign corresponds to what can be found in the literature and according to classic demand theory, right? So what this says is that percentage increase in percentage change in electricity price, for instance, will drive electricity consumption down by 0.13%. And then we see that electricity consumption is positively correlated to exports per capita and also GDP per capita, but then the coefficient of GDP per capita is not significant. Yeah. We also find, yes?
You have 3 minutes left.
Okay, thank you. So we also find that the coefficient of the error correction term is negative and highly significant, which means that the deviations from the equilibrium path are corrected up to 21% in the short run. And then moving to the long run elasticities, we see that GDPPC is still not significant, but then electricity consumption becomes more elastic to changes in price. So that could be explained by the fact that consumers have more time in the long run to adjust their consumption patterns, changing their lifestyle choices. And then electricity consumption becomes elastic to exports per capita. So this could be explained by the fact that Mauritius has transitioned from a low income agriculture dependent economy before its independence to a upper middle income open diversified economy, right? Thus resulting in increased electricity demand. So quickly, just presenting the two-diameter causality results, we did not find any causal relationship running from our explanatory variables to electricity consumption. So we conclude that electricity conservation policies do not hinder economic growth in Mauritius. Then, on the contrary, what we find is that the opposite in Sultan, so electricity consumption policies are detrimental to economic growth. So this highlights the importance of still investigating this the complex nature of the relationship between electricity consumption and other key economic variables in Mauritius, and calls for the re-estimation of the perspectives provided in Sultan, right? So to conclude, we found a unique and stable co-integrating relationship between our variables, which means that there is an error correcting mechanism, which puts electricity consumption back on its equilibrium path. In the short run and the long run, electricity consumption is price inelastic. So this can be explained also by the cross-subsidization policies that are put in place by the local network operator, and also the absence of causality running from explanatory variables to electricity consumption means that we can implement energy saving policies in Mauritius that correspond to the already announced objectives of putting in place energy efficiency measures. So a few limitations that issues with data availability, but this is the case in almost every developing country. And also the results might have been more nuanced if we had considered sectoral electricity consumption. So this is what we're going to investigate in the future, but also use the results in this study to enhance energy transition scenarios to be used in bottom-up optimization models. Thank you very much for your attention. So if you have any questions, I will gladly answer them. Thank you.
Thank you, Anna. Can you hear me?
Yes, perfectly.
Okay, I will start first. We can ask a few questions. It was very interesting. Thank you. What is difficult for me to understand is, of course, I can understand that electricity consumption is a function of economic variables, but it's hard for me when I read the abstract and even in the presentation to see the link with demand management. I don't see what could be the action of demand management. Of course, I see, but it's not easy for me in your presentation to understand this. And also, what do you think about renewable energy? Because it could shape the consumption in another way. In France, for instance, we know that renewable energy production and consumption will be very different.
Yes, thank you. So I'm going to answer your second question about renewable energy. So in the literature, people have also disaggregated electricity demand to renewable electricity consumption and fossil electricity consumption. But again, what we have found in the literature is that there is no consensus or whatsoever regarding the nature of the relationship, but also regarding the direction of causality. So it's kind of difficult to position our studies regarding the literature, right? But yeah, I've seen studies about renewable electricity consumption, but they are mixed results. And I think it would be interesting to study that in the Mauritian context. Thank you. And about your first question, I'm sorry, I didn't quite catch the first one.
I think because in the abstract you talk about demand side management, and I don't see in the paper or in the presentation the weight of demand side management in your study.
Yes, well, essentially what studies about electricity demand elasticity and causality results tell us is that when you do not have a causal relationship between, for instance, electricity consumption and economic growth, for instance, well, this means that if the government wants to implement energy conservation policies coupled with demand side management, then this won't affect electricity consumption, or this won't affect, sorry, not electricity consumption. This won't negatively impact economic growth, for instance, or even offset trade liberalization policies and trade gains. So essentially, that's why I was talking about demand side management, not including it in my regression, but mostly speaking of the potential impacts. So I advocate that Mauritius can move forward with energy efficiency measures and also implement demand side management to try to drive electricity consumption downwards.
Okay, thanks a lot.
Thank you. Do we have other questions?
So if we can go to the next presentation, if you don't mind. So the next presentation is about modeling the response of hourly electricity demand to climate conditions in Japan. And it will be done by, sorry if I don't pronounce well, Yuki Hiruta from Japan. Your micro is, we can't hear you.
Your mic is off. We cannot hear
Hello?
you. Oh, yeah.
Hello?
This is good. Okay.
Do you see full screen or the just developers mode?
We cannot see your full screen. We're seeing what
Maybe
you,
this is
the other screen. Oh yeah, this is good.
okay. Okay. Thank you for this great opportunity. My name is Yuki Hiruta, a research associate at National Institute for Environmental Studies, Japan. In this study, we propose a series of methods to simulate reliable temperature response functions for electricity demand at regional scale. From now on, let's call temperature response function TRF. Then, what is TRF? TRF is electricity demand as a function of temperature. They look like this, but horizontal axis shows temperature and vertical axis shows the electricity demand. Because we have cooling demand in hot season and then heating demand in cold seasons, they are usually shaped like the character U or V. And then balance point temperature. This is also important indicator. Sorry. Point. Okay, balance point temperature. This is also an important indicator because this is used as a reference temperature for heating degree days or cooling degree days, which are used for many studies related to climate and energy. And why it is important to generate reliable temperature TRFs? Because electricity demand affect climate condition through its generation process. And then climate condition also affect electricity demand by changing the needs for cooling and heating demand. So there are complicated interrelationships among meteorological conditions, human behavior, and electricity demand. So developing reliable TRFs are key for decreasing the uncertainties in both future climate projection and important impact assessment of climate change on energy systems, which are necessary for mitigation and adaptation measures against climate change. It looks simple to find the relationship between temperature and electricity demand, but actually, it is challenging because electricity demand determined by complex connections of multiple factors, such as timely human responses to given meteorological conditions. Therefore, the challenge is how to control the effect of factors other than temperature. So let's move on to the method. Target area is the jurisdictions of 10 major electricity power companies providers in Japan. What we've done in this research is pretty simple. We constructed regression models that explain hourly electricity demand by multiple factors, such as weather and daily routine cycle of human activities. And then we generated the TRFs based on the simulation by the constructed regression models. The key point is how well we can control the effect of the factors other than temperature using this simulation. They are the data and variables we applied to the models. Objective variable is the historical electricity demand, which is observed from the fiscal year 2016, from 2016 to 2019. And then as a candidate predictor, we applied historical weather data, namely temperature, humidity, solar radiation, wind speed, rainfall, snowfall, and snow depths. And we also applied the thermal comfort indices, discomfort index, and wind chill. Discomfort index is the indicator derived from temperature and humidity. And the wind chill are derived from the wind speed and temperature. We also applied the indicator for human activities. We applied the dummy variable that distinguishes the difference between the working days and no working days. We also applied the human activity data that shows the daily routine cycle of human activities. They are like this. And then with such variables, we constructed the regression model using the algorithm called MAS. Before we decided to use this algorithm, we examined the performance of other algorithms such as random forest and SPR, but the MAS performed better, so we selected this. So MAS can capture the complexity of the potential model by applying locally linear models. And MAS also can select important variables during the model building process. And MAS also has shown excellent prediction performance in short-term power consumption. So we selected MAS. And then we constructed models, and let's see the model performance next. The generalized coefficient of determination was from 0.870 in Kyushu to 0.953 in Okinawa. And this is a result from 2019, and then now the model is a little improved. And anyway, in these figures, the horizontal axis shows the observation, and the vertical axis shows the predicted electricity demand. And then, I'm sorry, it's hard to see, but there are two types of dots on the figures, black dots and blue dots. And black dots are the in-sample result, which are result by training data. Training data are the data used for model construction. And black dots are the, blue dots is the out of sample result, which are the result by test data, which are not used for model construction. So as we see this figure, we cannot distinguish the difference between black dots and blue dots in distribution, and they are all distributed around the 40-degree regression lines, and two regression lines are almost identical and cannot see the difference. So therefore, the constructed models are high quality in terms of both fit and generalization capability. This figure showed the predictions along the time sequence. The result for August in Tokyo are presented as examples. The hourly predictions, which is shown in blue, agree with observations, black dots observations very well. But we can see the little overestimate here, but we know the reason because these 2 days are the days between the consecutive holidays and weekend. So a lot of people take leave of absence, and then that is not considered by the data. So there are little overestimate, but we can improve this point because we know the reason. So on the whole, the hourly demand at regional scale are predicted almost perfectly. And then this table showed the predictors applied. As I mentioned earlier, math can get rid of the less important variables during the model building process. So let's see the variables remains. First, humidity was not applied in all regions. And then discomfort index was applied in all regions. This is likely because humidity better explains the electricity demand when it is factored into the models as a function variable of a discomfort index. And then snow was applied only in a snowy region, Hokkaido, Tohoku, and Hokuriku. And the dummy variable that distinguishes the working day and no working day are not applied only in Okinawa. This is because the main industry of Okinawa is tourism. So hotels and other facilities for tourists are active during the holidays. So there are less difference between working days and no working days. So that's why it was not applied. So the adapted predictors was pretty reasonable, I can say. So next, we simulate temperature response functions using the constructed models. In these figures, horizontal axis is temperature, shows temperature, and vertical axis shows the electricity demand. And the black dots are the observations. Now we can see the colorful lines. And this is the TRFs simulated by the model, constructed model. And then color difference shows the difference in hour. The first thing I can point out from this figure is the simulation result. Simulation results and observation demonstrate high compatibility, indicating the model will reproduce the relationship between temperature and electricity demand. In other words, the constructed models are high quality enough to simulate impact of individual factor, which is temperature in this case, on electricity demand by controlling the effect of other factors. And this figure, right-hand figure, shows the level of the BPT, which is the balance point temperature. This part is the bottom of the former figure here. And then this shows the change in balance point temperature. So we can not only the level of temperature we observed here, but also we can see the two different balance point temperature group here. So the in this figure, reddish line are concentrated on the upper part of the panel, and then bluish lines are concentrated in a lower part of each panel. So this indicates there are two different distinct TRFs in the daytime and nighttime. And then balance point temperature also indicate the two different TRFs. So so this indicates not only the level of the electricity demand, but also the functional form of temperature response function can be changed between the nighttime and daytime. Then we simulated daytime TRF and nighttime TRF. As we can see, high density ridges in this observation data is neatly covered by the simulation.
Sorry, Yuki?
Hi, yes.
You have 5 minutes left.
Okay. Okay. And then now we are able to obtain the two distinct TRFs in a daytime for daytime and nighttime. And this is good TRFs, but they are too flexible and complicated to be applied to other models. So we approximated the TRFs, and then we got parameters from the approximated result. We got the piecewise linear functions from the approximation, and then we got the parameters such as the coordinate of breakpoints and then slope of the partial regression lines. Then let's summarize. In this study, a series of methods to simulate reliable temperature response function is proposed. We presented the capability of the methodology and temperature segment in TRFs and parameters and functional forms of TRFs for 10 regions in Japan. And we have 4 suggestions for acquiring reliable TRFs. First, multiple factors should be modeled and controlled, and flexible regression method that can consider non-linearity and interactions should be used. And third, a small number of robust predictors should be carefully selected and applied. This is very important because it is if the purpose of the research is just predicting the electricity demand, it's okay to implement many predictors. But if the purpose is to identify individual factors' effect on electricity demand, we need to select the sound, robust predictor from the various possible predictors, which are usually intercorrelated. So the predictor selection is very important. Sorry. And then the fourth, detailed temporal resolution data is very important because the wide range of data includes the extreme condition can be considered, and the numerous combination of the multiple methodological data that are actually observed simultaneously give the information about the interaction effect to the model. So it's very important to use our detailed resolution data. And we also have 2 suggestions for the application of TRFs. Temporal segments in TRFs should be considered. And when it's possible, the direct prediction of electricity demand by our model will provide better results than using TRF generated. And the model constructed in this study can be used for many different impact assessment. For example, impact of multiple meteorological factors on electricity demand, impact of COVID-19 on electricity demand, and impact of future climate change on electricity demand. Actually, they are all the studies now we are working on. So thank you very much. It's all.
Thank you, Yuki. It was a very nice presentation, I must say. The second one, but this with a lot of graphs. And I've got only one question, maybe two. When I read the abstract, and I think it's at the end of the presentation, you talk about the long term. I mean, the climate change, we know that the weather will change, and with more extreme events, do you think it will be easy to use your model and to look at this extreme event, and as you know, there are so many different scenarios for the future. You will be able to choose the right scenario or to test all the scenarios. And
it's actually in our institute, mainly 4 scenario climate models are used. They are the climate models like this.
yeah, okay.
And then we also have some different RCPs like this. And then we can apply this model to the for the impact assessment of climate change on electricity demand. And then we found the hourly model can deal with the, how can I say, detailed combination of meteorological factors. So we can do the better prediction than the models we used to use. So am I?
Some other questions, or we go on the third presentation? Okay. So the next, thank you, Yuki.
Thank you.
Thank you very much. So the next presentation is on household energy demand in Uganda, estimation and policy relevance. And it will be done by Grace, Alinaitwe. I hope I pronounce well, but I don't think so. It's your turn.
Okay, I'm Grace Alinaitwe. I'll share my screen. Yeah. Oh.
Okay.
Okay, I'm Grace Alinaitwe from the Norwegian University of Life Sciences in Norway. And the paper is on household energy demand in Uganda. And mainly to say that the focus is on electricity demand in Uganda. Electricity has been found to have so many advantages. That is, it improves household welfare, and it causes economic growth. From literature, we've seen that. It helps to prevent environmental degradation, because in most cases it is renewable energy. And it helps to protect the human health, since indoor pollution is avoided. And in Uganda, most of the electricity produced is hydro, above 80% is hydroelectricity. But there are other forms of electricity like thermal and solar. So even with all those advantages, we still notice that there are so many people that lack electricity, access to electricity. And in Uganda, in the year 2015, only 22% of the population had access to electricity. And most of those were living in urban centers. And even those that were connected, most of them use it mainly for lighting purposes. A number of programs were put in place to try and improve the supply and accessibility of electricity, especially in the rural areas. But still, we observe that the connection rates are very low, with only 22% of people using electricity. On the other hand, we noticed that the installation capacity, the installation generation capacity is high in Uganda. Well, it is low if it is on per capita terms, but generally the installation generation capacity is over 1,200 megawatts, while the maximum peak demand is about 700 megawatts. So there is a gap between supply and demand. And that means we can use this opportunity to improve the welfare of people. So we could use the opportunity of this supply to improve on the welfare of the people. So somebody would ask why the gap is there. Some of the reasons, it's because of the transmission lines, they are not in place. So even when there is demand somewhere in the rural, people might not get the electricity because there are no transmission lines. The level of industrialization is low in the country. So, and many other reasons like those that are already connected, they use it just for lighting purposes. So the whole aim is trying to use this opportunity of this generation capacity to improve on the welfare of the people. So yeah, we will look at the energy demand consumption by calculating the price and income elasticities of these energy fuels. That is electricity. We look at mainly electricity, firewood, charcoal, and kerosene. They are the major fuels used in Uganda, mainly for cooking and lighting. So why are we interested in these elasticities? Because we know that if we need to look at any policies that will aim at either subsidizing the vulnerable household, or if we look at the energy utilities, like the distributors, they will require this knowledge. It will be of great importance when they're making dispatched decisions. So it is important. We must look at the welfare, if we must improve on the welfare of the country. So the results, we shall try to explain them, to analyze them using two theories, the energy ladder theory and the energy stacking theory. The energy ladder theory says that when people's incomes increase, people shift from the solid energy fuels like firewood and charcoal, and they move on to more efficient fuels like electricity. In Uganda, we observe most of the people are still using the solid fuels like charcoal and firewood. So we don't even know if this theory holds the country. Energy stacking theory says that when people's incomes increase, they don't actually abandon these solid fuels like charcoal, but they add on other fuels like electricity and use them simultaneously. So we don't know which one is supported or which one is true in Uganda. We use the Uganda National Panel Survey data from 2013 and 2014. And most of the variables that we get rid of after data cleaning, it is household survey data. Most of them that we eliminate is because they lack the basic information on household expenditure, but the data is rich in that it has most of the information on energy. It also has all the other variables on all the other control variables like household variables like the age, the size of the household, the education of each person. So the data has almost all the variables that we need. But the data does not have the prices of electricity. So we get that extra information from the Electricity Regulatory Authority and we complement it to the other data. To get the elasticities, we use the indirect utility function. We use the QUADS model, that is quadratic augmented my goodness, demand systems. So we use the indirect utility function. And when we apply raise identity, we are able to get the expenditure share of each energy function, of each energy, and of each household. So if you look at this, it is just J is for energy fuel, that is electricity, firewood, kerosene, and K is the household. So to derive this, we use the indirect utility function. And then Ray suggested scaling because households are different in size and all the other variables. So when we do the scaling, we just adjust the shares, the expenditure shares of this energy, how much you spend on each energy fuel. And we also carry out censoring because we realize that not every household consumes all these energy fuels. And that is due to so many different reasons like non-affordability, non-preference, or you just don't have the access. For example, if you don't have access to electricity, you might not consume it. And if we don't do anything about it, we will have a solution. So to avoid that, we do censoring of the data, whereby we run this model in 2 stages. The first one is the probit model. And from those results, we get the probability density functions and the CDFs, of which we apply to the second stage in the model, the AIDS model. So we do that just to cater for the differences in the consumption, and we do the scaling to cater for heterogeneity among the households. And now from the results that we get in QUADS, the formulas are already well explained in textbooks, but we are able to calculate the Marshallian price elasticities, of which we can adjust and get the Hicksian price elasticities. And we are also able to calculate the expenditure elasticity. So we shall go straight to the results, bearing in mind that our problem was that we needed to use the surplus demand of electricity that is available in the country to improve on the welfare. So we are looking at the elasticities to see how price changes affect demand of electricity. Maybe just to go back, somebody would think that when the prices are low, then using the demand and supply condition in the market then the prices should just go down. Electricity prices are not low in Uganda, and that is because there are these investors that have put in their money in the generation, and they expect a price that is above the risks that are involved, and also to get a return. So when they are calculating the price, they put all that into consideration. And then we end up having expensive electricity in Uganda. And so the market supply and demand does not determine the price, say. So we did data censoring, and that's why we shall see here that 44% had electricity. That is because we take only enumeration areas with at least one person connected to the grid. So we eliminate most of the variables that don't have all this information. So the 44 will not be in line with what I first said, that only about 22% have electricity, because I have eliminated some of the, in other words, the data set is now small. From the first stage probit model, we find that most of the control variables positively affect electricity consumption. In other words, living in the urban increases the probability of being connected to electricity. And so is education, age. This is the age of the household head. If you're old, that reduces the probability of being connected to electricity. Being male increases the probability of being connected. So these are the results from the first stage probit model. And we also noticed that being educated reduces the probability of using firewood or charcoal. And that is because when you're educated, chances are you're going to get a job and your income will be high and you'll be able to afford other cleaner fuels. Even then, when you're educated, then you have the opportunity cost of your time is quite high. So you're likely to adapt to all the technologies that can save time, like the cookers and the like. So being educated will increase the chances of connecting to electricity, but they reduce that of using the dirty fuels. And so are some other variables, like being in urban reduces the chance of using firewood. So from the first stage results, we are able to calculate the PDFs that we incorporate in our QUADS model. And then we get these results. We find that most of the results are significant, whether it is wood or kerosene. And that might be an indicator that probably in Uganda, most people use a mixture of energy fuels, because most of them are significant. But the whole aim is the elasticities that we calculate from the QUADS results. So from this second stage, we are able to get both the expenditure elasticities and price elasticities. So with the expenditure elasticities, we notice that most of them, all of them are greater than 0. So indicating energy is a normal good. It's normal in that when the price increases, then the demand increases as well. So whatever energy you're using, the price, when your income increases, the consumption increases as well. Yeah. But we notice charcoal has got the expenditure elasticity, which is greater than 1, which indicates it's a luxury good. And indeed in Uganda, from observation, when people are using charcoal, cooking with charcoal is preferred, and it is taken as more luxurious than using firewood or other forms of energy like crop residue. So even when you're living in the city, people still use charcoal. Majority, at least, they're still using it, even when they have connections to electricity. So having an elasticity of greater than 1 indicates that, but also it is evidence of energy stacking, in that even when you have your income improve.
Sorry,
Yes.
you have a few minutes left.
Yeah. Okay. Let's carry on. We also calculate the price elasticities from the COIDS results, both Marshallian and the Hicksian elasticities. Irrespective of the type, we see that own elasticities are negative. That is in line with theory. And the cross elasticities, if we look at I'll concentrate on electricity. If it's positive, it means the two goods are complements. And we find that electricity and wood, it has positive. It means electricity substitutes wood, and so other energy fuels. But when we look at kerosene using Marshallian, we find that it's negative, and that means it is not a substitute but a complement. And that is true that charcoal is used mainly for cooking, while electricity is used for lighting. So it complements charcoal. But using the Hicksian ones, which adjust for all the substitution effect of income, we find that they're all positive, which means electricity indeed substitutes all the energy fuels. It can be used for cooking, for lighting, and for whatever the other energy fuels can do. So if that is true, then we can say that, okay, yeah, we find that electricity substitutes all the other energy fuels because the cross elasticities are positive. And it is smallest for charcoal, again, indicating that people are ready to change from charcoal to electricity. What can we say about that, or recommendation? We can say that the government can intervene in different ways. One, by expanding the transmission lines, by reducing or freely connecting new customers, new households, and also monitoring the distributors to kind of make sure the price is not overpriced, electricity is not overpriced. And the government should encourage households to use other alternatives like solar, since it doesn't require the grid. And maybe for further study, it's about the policies that the government can make, because we are saying that if electricity can be cheaper, then people will shift because it substitutes all the other energy fuels. But how can the government do that? How can it reduce the price? For a developing country like Uganda, it's not easy to do subsidies. And if we think of taxing the other energy fuels so that electricity is relatively cheaper, again, that one becomes hard to implement, to tax, and also it will make the standard of living of the poor even worse because they are the ones that use charcoal. So that is what I would recommend for further study on taxation and subsidization possibility of electricity. Thank you.
Thank you very much, guys. This is a very interesting presentation because Africa is our future. We know that the population will be the biggest one before the end of the century. And you answered to my question with the last slide, where, because you talk about tax, so it's tax to increase the green renewable energy, but tax on fuel, tax on the dirty energy.
Yeah.
Yes, because it's always it's always hard to play with tax because, as we know, in the macroeconomic economy, when you play with tax, you can have effect on one side of the economy, and on the other side, people who are not going to be happy. For instance, in France, we have tax and we have the gilets jaunes. You don't know maybe, but we had big problem with tax. So
Yeah, that's why I
it's
said.
not really a question, but just a comment.
Okay, thank you.
Can I ask a question?
Yes, of course.
Yes. Thank you for your presentation, Grace. Well, about the energy versus the energy data versus the energy stacking theories, have you found in the literature strong empirical evidence about the energy stacking phenomenon being more common in developing countries compared to advanced economies, for instance?
Have I found literature?
Have you found in the literature strong empirical evidence pointing towards the energy stacking phenomenon more common in developing countries compared to advanced economies?
Well, I observed that in Uganda, but for the literature, I cannot say that I have found strong evidence, but I think it is true that people use a mixture of energy fuels other than completely abandoning one and going to the cleaner one. Yeah.
Okay, thank you.
You're welcome.
Okay, we can go for the last presentation done by Olvar Bergland. I hope I pronounced well, from the School of Economics and Business in Norway. Sorry, because I didn't say the title of or the university for other presentation. And now it's about a machine learning approach to demand response supply estimation. It's very rich, we will see, and I've got question, of course, after.
Okay, thank you very much. I hope you can see my full screen.
Yes, yes.
It looks good here. And unfortunately, I decided to start mowing the lawn outside my office, so hopefully that will not disturb you too much. So what I want to talk about today is about machine learning approach, or how to get to the demand response and how we can estimate that. Move that one a little bit. Okay. So this is joint work with Alan Love at the School of Economic Sciences in Washington State. I have a joint appointment there. And since this is a WSU funded project, I'm wearing the Washington State colors as not the Norwegian University of Life Science colors as Grace did. So as a background, as the energy systems are transitioning, one of the things we're looking at has been talked about here very quickly, decarbonization. We have a decentralization in the generating system with renewable energy sources. And at the same time, there's an ongoing digitalization of the entire electricity sector. So one of the other things is how do we manage this one? And often the demand response comes up as one critical component of managing the system when we have intermittent renewable energy sources. So with respect to the demand response, we need to engage it, we need to activate it, we need to harness it. And how do we get to this demand response, and how do we get to use it, and how do we enumerate it? So the starting point here, or key here, is what we want to say something about what are the consumption patterns, how much of that bond can we bring into a demand response setting, and how do we compensate that and think about that bond is we want to design contracts that capture this bond, but we don't want to have contracts which are irresponsibly expensive, and at the same time we want them also to compensate the people, the participants in a proper way. And in respect to demand response, if that's going to work, we need to have heterogeneity among the customers or the population. So I want to talk a little bit about the background for this project. We're looking at some data we're using for verification of the models we're working with, and then some results and a summary or a conclusion where we are right now. So when we talk about the demand response, in our setting here, we're thinking about how can we shift the load or shed the load among end users. And we want to minimize the impact of that load shifting or shedding on the comfort. So think about what we just heard about by Yuki a few minutes ago. And our focus is on this shifting being short term. 5 to 10, 15 minutes is probably what we're looking at. And if we engage someone in a contract, it's not a one-time contract, most likely will be repeated engagements. So what do I want to do with demand response? The key here is what we want to manage local grid capacity constraints, but it could also be a possibility of more system-wide price spikes or blackouts at the worst. But I'm not going to talk about that part. My focus would be on the other side. So this is a project funded by the Sloan Foundation, which deals with the contract design and market development for flexible electric power systems. And it's focused on the residential demand side. So we're doing this one at Washington State, and we have within a college of engineering set up so we can do a smart city test bed. And basically what we want to do is simulate what goes on in the city. Now, how do we know something about the customers? These days, many places we have different types of smart meters, which collect a bunch of data. And we want to look at how can we utilize smart meter data to do what we call a non-intrusive usage detection. Of course, we can go in, if we get the permission to go inside somebody's house and put in monitoring devices, but we don't want to do that. This smart meter data we are ultimately using is consumption data for 5 minutes intervals for all customers basically in this local area. So we have data for a couple of years for about 16,000 smart meters. And we want to model the individual consumption patterns and then detect, say, HVAC or hot water heater usage or something like that, which are prime candidates for demand response. So this one project has a number of steps. We want to detect consumption patterns. We want to estimate the reservation prices for changes in the load. We want to use that one to map population customer heterogeneity, construct demand response functions, and then design the contracts. And finally, if we have contracts, look at the take up and look at what the local utility can do in terms of assessing the impact on the local grid. I'm not going to talk about the latter parts. I'm going to talk about the first part up to constructing a demand response. Now, we are starting with some data, not from the local area, but from a project in Austin, Texas, the Pecan Street data. And that one has some houses in the street which are heavily wired, and doing quite a bit of research on electricity consumption or energy use in the houses. And it has extensive behind the meter readings. So we have, from their setup, very detailed information about what kind of appliances are using electricity at any point in time. And the publicly available data we're using has a 1-minute resolution. Okay. We're using this data in order for us to assess or check to see if our methods and techniques we're going to develop works. What kind of data do we have? The top one here shows the temperature in May of 2018. The middle one shows the load split between the total load, which is the black one. The blue one is air conditioning. This particular house has an electric car, which you can see at the bottom there, which can account for quite a bit of a peak consumption. Now, I'm not going to talk about the electric car and how we can integrate that one in demand response. That's a different technology, different opportunities. So I'm just going to leave that. We look at a little bit more detail. We see that the driver of electricity consumption for this particular house is the air conditioning unit, and it comes on every so often, and the load increases quickly. So how can we detect that? So that is where we started thinking about what kind of techniques do we have, and we picked up some inspiration from the literature on machine learning, where we wanted to model individual household consumption patterns. Now, machine learning or statistical learning is where we're starting out from. So we're going to pick up quite a bit from the computer algorithms used there. At the other side, we're going to pick from the econometric side, the structural model building. So we end up with this, what we call it, an oxymoron, which is structural machine learning. So let me explain how we do that. Consumption in a household depends on what the household does. We don't observe that. So we're going to model the activities of a household as a hidden state. So as activities changes in a household, the household is then transitioning from one state to another. We want to model that one as a time-varying hidden Markov model. In econometrics, Jim Hamilton, many years ago, has a regime switching paper. So that's part of it. What we're building on is also Benji Frascani's input-output hidden Markov model. And the consumption is then modeled as a switching regression model. We're using a Tobit model because even if we have continuous usage, sometimes the usage is so small we don't register any consumption during a particularly when you're looking at 1 minute or 5 minute intervals. So what is a hidden Markov model? So we have a state at time TST, and it transitions to another state possibly another state in the next time period. So we have these probabilities of change. In each state, we observe something, and that probability of observing something depends on the state we are in. So estimation of these hidden Markov models entails two things. One is the transition probabilities between the states, and second, given the states, what's the probability of observing something? Now, in a switching regression model, like Hamilton's model, we are then introducing covariates on what we observe. But the underlying Markov chain still has constant transition probabilities throughout the time. The input-output hidden Markov models is introducing covariates, which allows us to have time-varying transition probabilities. So we could have temperature, which makes the probability of turning on the AC more likely. And that's where we want to be, because we think that temperature, time of the day, time of the week, as we just learned, is important for the consumption, and in our case, is also important for the states we're looking at. So that what we spent most time about is model estimation, how to develop that. So we have observed outcomes, which is regression models, so switching regression model. The state transition probabilities were modeled as a multinomial loaded model. And the joint estimation of all these parameters are fairly standard in principle by the EM algorithm or the Baum-Welch version of it. Fortunately, we can't use the standard software, so we needed to develop all the code ourselves. Now, if we're looking at transition probabilities, so at time t, we have a different states. We could end up in a particular state Si, coming from anyone in the previous period, and we move on to the next period, and we could end up in anyone. So a multinomial loaded model as a side issue is a way of saying, given that we in time t is in state Si, I want to model the probabilities of going into states S1 and so forth in the next period. We do that one through a multinomial loaded model. The difference here is that the standard statistical and econometric software would say that we know that you went to, say, S1. Here, we don't know that. We know that we went to S1 with a certain probability, which is less than 1, went to S2 with some probability. So we cannot use the standard software. The EM estimator is now an iterative process where we're iterating between estimating transition probabilities, estimating the different consumption functions, and updating our hidden Markov model, and it keeps on going like that until we reach convergence. So what do we get of our results here? So we predicted consumption, applied our model for 24 houses from the Beacon Street data, and focusing on the summer months. That's where the grid is strained. That's when the AC is on. Last winter, so this winter's events in Texas is not a concern for us. So we end up with having about 200,000 observations for each house. We typically estimated with 6 to 8 states, which appears to be fairly sufficient. We get the predicted consumption in each state, get the predicted probability of being in a particular state, and that gives us the average prediction at a particular point in time. So in terms of prediction, much better. So we put together here the blue line is the predicted load, and the red one is the total load. And the top one, there's only a few times you can see the difference. In the bottom line, there are certain periods when the actual load is fluctuating a little bit, while the predicted one is much more even. So from these houses, we can, for most of them, easily identify when the AC is on. There's a couple of houses which have very different patterns, but that's part of the game here. Because what we wanted to do is to say something about what are the actual candidates for demand response programs. If we can't identify you as having an easily, we would basically drop that household from consideration. So we can fairly easily identify and fairly securely identify that the different ones. I'm going to skip this one. Now, how does demand response work in this case? We're going to say, what happens if we say you can't turn on the AC? That is, we're going to take some states away in some period. We can get new predicted probabilities. We can get the new average prediction, and the difference between the prediction when we have all states available and when we have a limited set of states available, that's the change in the load. So that's it. We can now try to value that bond in terms of foregone opportunities and what kind of valuation do we have on that. So in order for us to predict the demand response, we're going to consider some situation with different covariates, say in afternoon when it's warm. We're going to predict the probability of the different states as a limiting distribution of a Markov chain. We're going to predict the quantities. We're going to predict the probability of AC being on and the predicted expected load from just those states. And we do that on households, and that results in some demand response curve. So we look at the temperature on y-axis and the probability of AZ on for these 22 houses. The probability is increasing. Good. And the expected load from these states is also increasing. The quantity is increasing slightly, and the probabilities of being in one of these states is increasing. So this represents the quantity available for us to possibly take out. And if I combined that, the expected quantity I can take out on the x-axis and the implicit valuation on the y-axis, I get basically the supply curve of demand response. And here for 3 different temperatures, and lo and behold, as the temperature is increasing, the supply curve is shifting out and making more available, although part of it is quite expensive to pick up. So from here, I think we learned that smart metadata is an emerging data source which we can use. One of them is when we look at the demand response. And I think we have shown that these input-output hidden Markov models can be used to detect consumption patterns. We can identify certain patterns which are interesting in terms of demand response. So we can use this one to say something about what does the demand response supply functions look like. And where we are now is designing the contracts on those potential participants we have identified. Now the next step is to look at how well, or how does this help the local utilities in terms of managing the local grid. And the bottom line there is that smart metadata allows you to know your customers and thus to look at if you can do your tailored products for those. So thank you very much. And if you have any questions, I think we will could be time for.
Thank you very much, Olvar. Can you hear me?
Yes.
Yes. It was very interesting and technical. As I say, it's not my field, but I've heard a lot about machine learning. I've got a specific question because, of course, I work at EDF. So you said that the model is capable to reveal the underlying drivers of the consumption level. And I was wondering that the pattern, sorry, the pattern can be modified by the pattern can be modified by reward incentives, tariff, services. So there are a lot of things we know that can influence the pattern, the demand. So do you think you are able to isolate each component to perform a breakdown of what's going on what is driving the demand with your model? For instance, the tariff and so
on. To some extent, but I'm not sure we've tried this data and certain, say for the household, certain appliances and things like that have fairly specific, call it fingerprints. So we can identify some of those. And that's our purpose. We're not looking at totally mapping what goes on in your house just by looking at your smart meter data. But if there is a hot water heater or an AC unit coming on and off, we are pretty good at detecting those and having an assessment of when does it come, what's the probability that it will be on at a particular point in time. And if we tell you to, or we turn it off, what kind of reduction in the load will we see? So that's that has been our goal, to be able to say that, not exactly what else goes on in the house.
Thanks a lot. Very interesting. By the way, I will send you an email to get more references to share with you your work.
Sorry.
By the way, I will send you an email to have more references.
Okay. Yeah, please do.
Any questions? Okay, so I must conclude, I think. 4 presentations, very rich, as I said, and with different problems, different area of the world. We have a lot of challenge in the future. Sorry, it's my daughter. And I hope to see you in the next conference. Have a nice day.
Just for the speakers, I just remind you to upload your presentation on the dashboard as soon as you can. And that's it for me. Thank you very much for the presentations.
Thank you, Jasmine.
Thank you.
Thank you.
Thank you. Goodbye.
Bye.
Bye.